Okay, so section 3.3, it's a bit on the long side. It's the last long section in chapter 3. The next two sections, 3.4 and 3.5, in the review aren't as long. So I'm going to skip the reviewing part of section 3.2, kind of finding the domain and range from pictures. Hopefully I did enough of the graphing problems that you're good at those. But if you're not feeling good about 3.2, you can kick me out an email or come visit me in my office and I can help you out. In section 3.2, one of the very first things I did is I said a relation is just a group or a set. They're kind of interchangeable words. Set is a more mathematically precise word. Of points. And again, a more precise, a nicer word for points is ordered pairs. In this section, we get a new word, and it's a function. And a function's a special type of relation. So it is just a group of points. In which no x is duplicated. So, specifically, if a given relation, if every point in a given relation has a different x, that specific relation, is a function. And it's probably more mathematically elegant to say, we say y is a function of x, when in a relation every single x is different. I don't have duplicate x's. Functions get us into that horrible notation, so that we start having function notation. So this is function notation that you might be vaguely aware of, and in a little bit I'll talk more about function notation, but I'm not ready for that yet. But the word function gives us function notation that you may or may not be familiar with, and it implies that I don't get duplicate x's, and let me show you specifically what I mean in a few problems. So the first few problems in section 3.3, specifically problems 1 through 6, they give me relations, finite relations that are just defined as a set of points, and I'm asked which of these relations define y as a function of x. And very specifically, a relation defines y as a function of x if every point has a different x. So as I look at the relations, if in a specific relation every point has a different x, then that relation is a function, and we say y is a function of x. If in a relation we have duplicate x's, then that relation is not a function. It wouldn't be correct to say y is a function of x. So if I look at the x's in problem 2, which is the first relation that's given on this page, because each of those numbers is different, 6, 7, and 8 aren't the same, I'm not looking at the y's at all for determining whether the relation's a function or not. For this problem, because all the x's are different, I'd say for this relation, y is a function of x. in my answers, I think I got real lazy, and if y was a function of x, I just wrote yes, and if y wasn't a function of x, I wrote no, which probably is not the best answer, but it's what I did. The next problem is a finite relation with only 2 points, and if I look at the x values, because the x values are different, this relation is also a function, or we can also say y is a function of x. And then again, if this was my answer key, I might just say yes, this is a function of x. Problem 6, on the other hand, it has 2 points with the same x, so it's not the case. So y is not a function, or y is not a function of x. The of x part we usually don't say. Only maybe at the beginning of introducing the concept of functions do we tack on this of x part. It's probably more common to say y is a function, y is a function, y is not a function, and that of x part is generally just assumed. And then for problem 6, I might have just said no on my answers if I was being lazy like I think I did. So the first 6 problems just want me to be able to differentiate relations into functions and not functions, and that's real easy to do. You just look at the points. If there's all the x's are different, then that relation is a function, or that relation y is a function of x. And if you have duplicate x's, then y is not a function. The next few problems ask the same question, but they give me a little hint as what to do. It says use a vertical line test to determine whether the relation defines y as a function of x. And very specifically, given the graph of a relation, that's what I have above here, the vertical line test, as opposed to horizontal line test, will help you determine if y is a function of x or not. And very specifically, if a vertical line can be drawn to touch the graph more than once, y is not a function of x. So I'll give you a second to look at that, and I'm going to pull out and do a makeup problem or two, because I only want to do the even problems, and the even problems aren't as interesting as the odd problems. So I'm going to make up some problems and explain to you why this vertical line test works, or how it's related to the first 3 problems that I did. So each of these are graphs of infinite relations. They have infinitely many points. It's impossible to list all the points, because any place where you can make a dot, there's a point, and every point has both an x and a y coordinate. I can't list infinitely many points. So it's impractical, or it's impossible to list all the points. So using the strategy that I used for the first 3 problems, I can't use. But I can use another strategy. And let me do a made-up problem similar to these. So this is just an extra made-up problem to help you understand the vertical line test. And in fact, I'll do a few extra problems. So I'm going to draw a picture of a U on its side, more or less. So if this was one of the problems between 7 and 12, and I was asked to use the vertical line test to determine whether this is a function or not. Real quickly, because I can draw a vertical line to touch the graph in more than one place, we'd say this y, for this particular relation, y is not a function of x because, I don't need to write the because part, because we said, but because it fails the vertical line test. By failing the vertical line test, it means I was able to draw a vertical line and touch the graph in more than one place. So I'm done with this problem. There isn't anything more I'd have to do, but I want to explain how the vertical line test and duplicate x's are related by writing the coordinates of the points that my vertical line went through. Any place I can draw a dot on this graph is a point that's part of the relation. There's infinitely many points, but this point right here, which is the point 3,5, is most certainly a point on that of the relation. And this point down here, the point 3, -2, which are the 2 points on the relation that the vertical line touched, these 2 points have the same x's and they're both part of the relation. So what a vertical line test does is it finds points that have the same x's, because any place where a vertical line touches a graph is a point on the relation. And if you can make a vertical line touch more than once, then you have points with the same x, and then that's not a function. Let me do a couple more before I get into the handout, because I don't think I had enough problems in the handout that were odd problems. These aren't particularly hard, but I just want to do them anyways. I don't really need to label any points when I do this. So this is kind of a half a U on its side, and no matter where I draw a vertical line, any place I can draw a vertical line on this graph, it only intersects the graph one time. So because it's impossible to draw a vertical line to touch the graph more than once, I can't find points that have duplicate x's. So we say in this case, y is a function of x. And again, parenthetically, because it passes the vertical line test. If you went up high enough in math in high school, you might remember a horizontal line test, and we'll get to a horizontal line test. I think it's in chapter 5. The horizontal line test is similar to the vertical line test, but it tests for something different. If you can draw a horizontal line to touch the graph in more than one place, it doesn't make it not a function. It's still a function, but functions have special types. There's one-to-one functions and not one-to-one functions, and the horizontal line test has to do with functions, breaking functions down into categories. But the horizontal line test has nothing to do with figuring out whether something's a function or not. It's when something is a function, what kind of function is it? And you don't have to remember the horizontal line test, and we won't get to it for a while yet because it's in chapter 5. One more problem, and then I'll do the 3 even problems in the handout. So let me make this. Nice V. I could tell you what the equation of this graph is, or I can make a good guess at it, but what I have to do now is figure out if this is this is definitely a graph of a relation. Is this a relation a function or not? It is a function if it passes the vertical line test. It's not a function if it fails the vertical line test. And as I look at the graph that I drew, I don't think it's possible to draw a vertical line to touch the graph in more than one place. So in this one, we'd say y is a function of x. And I'm almost certain that I got ultra lazy, and my answer would be yes if y is a function of x, and no if y is not a function of x. Let me do one more before the handout. And if you want to fast forward through this, be my guest. It's completely fine. Let me do this. Well, that looks the same. So we'll do that graph. And for this graph, because I can draw a vertical line that touches the graph in 3 places, that's as bad or worse than touching it in 2 places. For this graph, we say y is not a function of x because it fails the vertical line test. And then again, I might just say no for an answer, meaning no, it's not a function of x. Okay, now the 3 even problems between 7 and 12. I'll leave you the odd problem 7, 9, and 11 to do for homework. And for each of these, I'm just going to say yes or no. Yes if y is a function of x, no if it's not a function of x. And the reason I did extra problems is because I don't have very interesting problems between the evens in 8, 10, and 12. If I look at problem 8, it's impossible any place I draw a vertical line. It only touches the graph once. So this passes the vertical line test, and we can say yes, or we can say y is a function of x. Similarly, number 10, all the vertical lines that I can draw, if they're perfectly vertical, they're only going to touch the graph once. So I can say the exact same answer, yes, y is a function of x. And then problem 12, I mean, there's some room for debate. It's clear out here that these lines only touch the graph once. It might not be so clear around the origin what's happening there. I intended this to be a yes. I intended the lines real close to the origin to still only touch the graph once, but right at the origin you can't really tell. This is not the best equation. I probably should have changed it before I just did this lecture, but I didn't. I intend this to be yes, a y is a function of x. But if you said no because you thought one of these lines touched the graph in more than one place, I can live with that as well. I wouldn't put this kind of problem on a test that there might be some, debate. Whereas the problems 7, 9, and 11, there's not supposed to be any debate on those. When you go to do those for homework, it should be clear which ones fail the vertical line test and which ones pass the vertical line test. Okay, so far not a bit of algebra, but we're getting to the algebra part. And we're getting to the algebra part, and the algebra part where I need to review a little bit. So before I do the problems between 13 and 30, which get us into the function notation, I'm going to compare. I'll call it XY notation to X f of x notation. I'd call this function notation. So this is function notation. This is just non-function notation. Function notation definitely has its place. Most students generally don't like function notation, and I can completely understand that. It really wasn't until I got into grad school and had to do some really precise proofs that I started to appreciate the beauty of function notation. When you're writing mathematics and proving things mathematically, function notation just makes it easier to write mathematics nicely. But it's a bit confusing when you first get exposed to it. Theoretically, if in your last high school class or if you took beginning algebra, you saw function notation. So hopefully this is the second time you're seeing function notation and that you have a little familiarity with it, and that my reviewing it makes you understand it even better than you did before you started watching this video. So this is a completely made up problems. For a mathematician, these two problems, y equals 2x plus 3 and f of x equal 2x plus 3, have the same meaning. The f of x symbol and the y are kind of equivalent to each other. The y and f of x symbol are equivalent. And it is okay to replace an f of x symbol or function symbol or function notation with the letter y. So I can actually probably read both of these, y equals to 2x plus 3. The reason we use the function notation is because it makes it easier to ask questions and it makes our answers more clear. So if I'm going to ask a question related to this y function, this y equation, and if I'd say evaluate when x equal to 4, that's something we did in section 2.1, and hopefully you remember how to do that. When I evaluate with x equal to 4, what I'm doing is getting a point on the graph. And algebraically, I would do this. And my answer to evaluating when x equal to 4 is y equal to 11. The nice thing about function notation is it makes it easier for me to ask questions, and it makes my answer in some sense superior. When I look at the answer to this question that I just asked, I can't tell what the question was at all. In function notation, this same question can be asked using function notation. So if I saw this right here, this means, that symbol means evaluate when x equal to 4. Generally, when I'm dealing with functions, a number inside the parentheses is the number you're going to change the x to. So let me go ahead and do this. F of 4 is going to equal to 2 times 4 plus 3. And then it's 8 plus 3, which is 11. So my answer to this, I'm going to write f of 4 equals 11. If I just looked at the two answers, if I looked at the answer to the first problem that I made up, evaluate when x equals 4, and I look at the function notation, both answers I know what y is equal to. In regular xy notation, when an equation is solved for y and you plug a number in for x, it's clear that that says y equal to 11. But by looking at that answer, I'd have no idea that I plugged 4 in for x. Function notation, although it's kind of hard to get used to, the number to the right of the equal sign stands for a y value, and the number in the parentheses is the x that gave that y. So I can tell I plugged in 4 for x to get y equal to 11. So in function notation, generally the number inside of parentheses stands for an x value, and the number to the right of an equal sign stands for a y value. So in general, that's probably something real important that makes function notation so useful. So function notation, and the letters don't have to be x. f of, like, if I said f of 7 equals to 23, the number in the parentheses is generally an x value. The number to the right of the equal sign is a y value. And so this kind of shows a point, 723. So in function notation, the number inside a parentheses, or the parentheses, and I'll say is usually, it's not 100% of the time in our class, it'll be 99.9% of the time, is usually an x value, and the number to the right of the equal sign is a y value. And I absolutely don't have to use the letter f. I can usually use, functions are named with small letters. Like if I wrote something like this, g of -1 equals to 6. For that notation, the function's name is g, and I know that when x equal to -1, y equals to 6, and this kind of points to the point on a graph, -1, 6. So function notation, really, the function symbol, if you wanted to, you can change any function symbol to the letter y. Those have the same meaning. The superiority of the function notation is it makes it easier to ask the question. To ask you to evaluate when x equal to 4 without function notation, I have to write those couple words in the number. In function notation, the question evaluate when x equal to 4 can be shortened, so it's a shorthand, which is, mathematicians prefer. And when I look at my answer, I see the question, when I evaluate when x equal to 4, I get y equal to 11. So it's just a superior notation. It's infinitely better than the y notation, but it's hard to get used to, and it's often harder to do algebra with function notation than it is xy notation. So sometimes, especially when we get like into section 3-4, I'll be given function notation, and I'll take the liberty of changing that function notation back to y notation, because for certain algebra problems, function notation, if you leave something in function notation, it's just kind of messy to use. Okay, so that's just the briefest review of function notation. It'd be nice if you know all that. A lot of it's going to come up again when we do problems 13 through 30 and the rest of the section. So if you're not completely understanding function notation, what you're going to need to get out of function notation, you'll get as I do the problems. So the instructions for problems 13 through 30 said consider the functions defined by and find the requested values. And I give you 4 functions, a function called k of x, f of x, g of x, and h of x. And each problem only calls out one of the 4 functions, and it wants me to change the letter x to a number or a letter and simplify. So in problem 14, I'm going to use the f of x equals 3x plus 4 function, and to find f of -2, I'm just going to replace the x with -2, and I'm going to simplify. So I'm going to get f of -2. I change the x to -2, and I do orders of operations. I'll cheat. I'll use my calculator. And this is kind of insulting to use my calculator for this, but I'll save ink. So I get -2 when I do that, because this is -6 plus 4, which is -2. I'm done. This is my answer. This would be the best answer. It would be okay if you just wrote the -2 that's to the right of the equal sign. And that's all there was to do for problem 14. In fact, most of the problems between 13 and 30, especially the problems that have numbers in the parentheses, are going to be really quick one-step problems or two steps. Once I start putting letters in the parentheses, they're a little more confusing, but not too bad. So problem 16 calls out the g function. So I have to know what the g function is, and that's going to change from problem set to problem set. The g function isn't like exclusively x squared plus 5x plus 6. When we do a problem in another section, I might use g of x for a function name and not make it x squared plus 5x plus 6 anymore. 16 wants me to find g of 0. To find g of 0, I change the x's to 0, or evaluate the g function when x equal to 0. And I do the arithmetic. I hardly need my calculator for this, but I could use it if I'm just really bound to the calculator. I can go 0 squared plus 5 times 0 plus 6. It's going to give me 6 because this gives me g of 0 equals 0 plus 6, which is 6. So the best answer would have both the problem and the answer next to each other, but it would be okay if you just wrote 6 for your answer. It's nice here because I can tell you when x is 0, y is 6. It would be wrong to say x equal to 6 because that's not an x value. 0 is the x value, 6 is the y value. So if you wanted to attach a letter other than a function name, you can always change any function name to the letter y, so it'd be okay to say y equal to 6. So you need to understand that that number to the right of the equal sign that I get when I plug a number in for x is a y value and not an x value. So that's why it would be wrong to say x equal to 6, because x is 0 and y is 6. The number inside the parentheses is an x value. The number to the right of the equal sign that I get is a y value that corresponds to that x. Really a point on the graph of that function. 18's a mess for a lot of students. When we did the last problem, it wasn't so hard for me to find g of 0. I changed that x to 0. I changed that x to 0. I left the 6 alone because I didn't have an x. The next problem, it's not supposed to be harder. It's actually supposed to be easier. I'm going to treat the 4 in the next problem like I did the 6. I can't change a number without an x to a number inside the parentheses. I only change x's to the numbers in the parentheses. And when I do problem 18, I look at the function h of x. We call that a constant function because it doesn't have an x. There's no place to put an x. If you really needed, you can think of h of x having an x. You can rewrite it as 0x plus 4 because that's the same as h of x equals to 4 because 0x is 0. And then you can go h of 3 equals 0 times 3 plus 4, which is 0 plus 4, which is going to be 4. But this is kind of overkill. It's assumed that if there's no value for x, there's no place to put the number, and the answer is going to be constantly 4. Which is why we call it the constant function. No matter what letter or numbers in the parentheses, I'm just going to get 4 out. And again, it would be okay to say y equal to 4. It would be wrong to say x equal to 4 because x doesn't equal to 4, x equals to 3. It's x equal to 3, y equal to 4 because the number inside the parentheses is the x value, the number to the right of the equal sign is the y value. Is the last one for a while. I think that you still get to put a number in for x. I'm going to go to the k function, which is 5x squared, and change the x to -6 and watch my orders of operations because I need to do exponents before multiplications. So k of -6 is going to be 5 times -6 squared, and it's only the -6 that gets squared. It's not the 5, because the only thing that gets squared in the k of x is the x. The 5 doesn't get squared. I would have written it as 25 if I wanted you to square the 5 every time. So when I do my orders of operations, my calculator won't let me down if I use a parentheses for the x. Tells me it's 180. Without my calculator, -6 squared is -6 times -6, which is positive 36. So orders of operations want me to do exponents before multiplication, and you get k of -6 equals to 180. This is the best answer. It's also okay just to write 180, or it's also okay to write y equal to 180. It wouldn't be correct to say x equal to 180 because x is -6. So up to 20, this grouping of problems is moderately friendly. The h function's a little bit tricky because it doesn't have an x, but when you have numbers inside the parentheses, eventually most students get the answer correct. The next few problems have letters inside the parentheses, and when you have letters inside the parentheses or variables inside the parentheses, students start to do bad things because they want to do more than they have to do. So in problem 22, as well as 24, inside the parentheses, I'm supposed to change the x to the letter C. So that's what I'm going to do. I'm going to do problem 22 much the same that I did problem 14. When I did problem 14, I put a -2 where the x was. I put it in a parentheses to signify the multiplication, and then I just simplified using orders of operations. That's all I'm going to do here. Is just my first step's going to look just like this first step. So inside the parentheses is a C. I'm going to change the x to a C, just like I changed the x to a -2 in problem 14. The thing about 22 that makes it a lot different and a lot easier to make a mistake is there's less to do, and a lot of times students overdo it. Two things students do that are wrong I'll talk about in a second. This is actually an okay answer. It turns out that if I had the 3 and the C written next to each other without the parentheses, that would still mean 3 times C, and it's a cleaner way to write it. This is actually the end of this problem. What I do is I change the x to the number or letter in the parentheses and simplify as much as I can. Well, in the last few problems, I could simplify quite a bit because everything was like a like term. Here, 3c and 4, you can't add those to get 7c. So these aren't like terms. This is actually the best answer to this. It's harder to, to visualize this, but that is the best answer. It would be okay if you just wrote 3c plus 4. It would also be okay if you said y equal 3c plus 4. What would be wrong, and which is probably the most common mistake, the worst thing you can do is to take a correct answer and make it so you lose points. And it just, for whatever reason, students just feel they have to do this, and I'm not sure why, but it's real common. When we do the test over chapter 3, usually at this point in the semester, if the class starts with 30 students, there's 28 left or so, I would guess 6 of the 28 will do this. They'll take the answer when you plug a letter into a function, and they'll set it equal to 0 and solve for the letter. That turns out to be absolutely wrong. And I'm not sure why students do it other than it just looks tempting to do. You do not, you should never, or should, in this case, do not set this equal to 0 and solve for x, or solve for c. Actually, what you're doing when you set it equal to 0 and solve for c is what you're actually doing is you're finding an x-intercept. This right here, this algebra, or this is the algebra needed to find an x-intercept in a really odd way. And nowhere in the instructions did I say anything about finding an x-intercept, so setting it equal to 0 is just wrong to do completely. And if this was a test question, a nice one-step test question where I'm trying to be kind, maybe worth 4 or 5 points, and you get the right answer and you set the right answer equal to 0, and then all of a sudden I'm going to take at least half credit off. So when we're just evaluating, putting numbers or letters into functions, you're not getting an x equal, you're getting a y equal, and you never, if your answer has a letter in it, do you set that equal to 0, unless you need to find an x-intercept. And we're not finding x-intercepts, so would be the wrong thing to do. So 24 is a little more complicated, but not that much more complicated. What I'm going to do in 24 is change, just like I've been doing with the f function, I'm going to change the x to b minus 2, and I'm going to simplify and combine like terms. Because there's a letter in the parentheses, that letter is probably going to be in my answer. So I'm going to write f of b minus 2. I'm going to do the operations, multiply 3 times b and get 3b, 3 times minus 2 and get minus 6. I'm going to combine the minus 6 and the minus 4 to be a minus 2. And I get 3b minus 2. This is the very best answer. Again, it would be okay if you change the function symbol to the letter y, because those are interchangeable. Or it would be okay if you just wrote what's to the right of the equal sign. It would be very wrong. So I'm doing it in a different color. If you got the right answer and you took the time to set it equal to 0, again, that's the strategy that we need to find an x-intercept. Turns out that if I graphed, well, I don't even know that. It's maybe more abstract than that even here. At best, this finds an x-intercept. I don't even think it finds an x-intercept here. So you do not, when you're evaluating a function, add a letter. You don't set it equal to 0. And again, if this was a 4-point problem, fine. If you got there and stopped, you'd get all 4 points. If you took your answer and set it equal to 0, bad things would happen, and you'd start losing points. (26) is tricky. Calls out the g function, which is the most complex of the 4 functions. It wants me to change the x to 3a and simplify. G is factorable. If I factor g before I plug the 3a in, I'm going to make my simplifying a lot easier, but I'll pretend that I wasn't so slick, and then I'll show you. Well, at least I'll do it just the old-fashioned way. So that's technically finding g of 3a. I'm supposed to take any x in the g function, change it to 3a, and now I'm going to simplify using orders of operations. First I'm going to do exponents. The exponent wants me to do 3a times 3a, and 3a times 3a is 9a squared. You multiply the 3's together and get a 9. You multiply a times a and get a squared. The 5 times 3a is a 15a, and then the plus 6 is a plus 6. If you have a polynomial for an answer and you don't factor it, I'd probably take a point off if you didn't go and factor something that's easily factorable. So this would be a -1. It's a correct answer if this was a test answer. The reason it would be a -1 is because this is factorable. it's clearly as a common factor. So if you at least took the step to find a common factor, I would be less likely to take a point off. I'd probably still want to take a point off. That's a better answer. But anytime I have something with a square, I should see if it factors. So off to the side, I'm going to try to bottoms up this and see if I can get the best answer. So I'm going to take this 3a squared plus 5a plus 2 and try to bottoms up it. I'm going to multiply the 3 and the 2 and get 6, because bottoms up, you multiply. Magically looks like that. You factor. That factors into a plus 2 and a plus 3. And then you divide, reduce, and bottoms up. Dividing by, I multiplied the last thing by 3, I divide the last thing by 3. First fraction doesn't reduce, I bottoms up. Second fraction does reduce, I get a plus 1. The answer that if this was a test question that you'd get full credit for and not lose a single point is leaving the common factor of a 3 and making two parentheses, one with a 3a plus 2, the other with an a plus 1. This is the best answer. Absolutely would get full credit for it. And again, it would be okay if you wrote y equal to 3 times 3a plus 2 times a plus 1. And it also would be okay if you just wrote 3 times 3a plus 2 times a plus 1. Any of these things that I wrote okay for, I wouldn't even take a point off. If you took the parentheses and set the inside of the parentheses equal to 0, then you start losing points. When we're plugging letters into functions, you don't take your answer, set it equal to 0, and solve for the letter. Two more of these problems, I believe. 28 and 30. 28, I would be surprised if I put it on a test, but if you're taking Math 151 or any calculus class, this sort of substitution comes up so often that you should just get good at it. And if you're working ahead of me, it's a beautiful thing to do. I prefer it when you try to work the problems before me and then check to see if you did them right. If you're working ahead of me, there's a good chance that you mess up the exponent. So that's technically what I'm supposed to do. I'm supposed to use the g function and change the x to an x plus 1 and simplify. I do exponents first, and if you don't match up with my answer, my guess is you blew this exponent, because something to square x plus 1 means to multiply x plus 1 times x plus 1, because squaring anything means to multiply that thing by itself. And x plus 1, it doesn't look like it's a foiling problem how it's written, but when you expand it, you can see it's a foiling problem. And to properly expand that exponent, you have to FOIL. So for g of x plus 1, I'm going to first change the x's to x plus 1. Then I'm going to do the exponent. The exponent involves FOILing. So the x plus 1 quantity squared, you get x squared plus 1x plus 1x plus 1, or x squared plus 2x plus 1. So I did my exponents first. Now I'm going to do this multiplication of 5 times x and 5 times 1. And I'm going to bring down the plus 6. I'm almost to a point where I have an answer that is nice, but probably can be factored. So I'm going to combine like terms. The x squared, there isn't another x squared term. I know it's just going to be part of my answer. But the plus 1x, you don't need to write the ones, but I like having them. It makes it easier for me to simplify. The plus 1x, and plus 5x combine to be a plus 7x in my answer. And the plus 1, plus 5, and plus 6 combine to be a 12 in my answer. If you stopped there, I may not take a point off. But I probably would take a point off. Sometimes when I'm grading, If I sense the test scores are really low and students are doing poorly, then I get kind and I don't take a point off like that. But if, like, out of 28 students, I feel like 24 of you are going to get A's, then I start searching for points, and I'd probably take a point off for that. In general, I always should take a point off, but in reality, it changes from test to test. So sometimes you might get away with not factoring and still getting full credit. So this x squared plus 7x plus 4, that definitely factors, and it's easy factoring. I don't need bottoms up. There's no common factor. My first are a couple of x's. My last need to multiply to 12 and add to 7. They need to be 4 and 3. So this would be the absolute best answer. If you wrote negative 4 and 3, you'd lose points. So you would lose points. You'd get like a -2 if you, and you'd lose points if you did too much. And the too much, it would be to take the parentheses and set them equal to 0. Again, that kind of finds, it's a strategy for finding x-intercepts, but I'm not even sure in this particular case that's even finding an x-intercept. In fact, I know it's not. So when we're dealing with evaluating a function, add a letter. That letter's going to be in my answer. I'm not going to take my answer and set it equal to 0. If I have to or want to, I can change the function symbol to y, or not write the function symbol at all, and that's okay. When not, you'll get full credit if you could actually read that. That says y equals x plus 4 times x plus 3. You get full credit for that. Last even problem, k of a minus 2. This is similar to the last problem, because when you have a square in a binomial, you're going to need foiling, and you have to watch your orders of operations. So I'm going to call out the k function, and I'm going to change to that. That's actually factored already. If I didn't multiply this out, that's actually not a bad thing. If I do multiply it out and refactor it, I'm going to get right back to where I was at. So the difference between the last problem, I had 3 individual pieces, and I wanted to get it down, everything gobbled up into parentheses and nothing outside separate from the parentheses. It would be okay in this problem to stop here. It's actually a good answer. It's factored. And that's not a bad thing. But if you started going further, this is how you'd go further. So the difference between the last problem is there's more. The right side wasn't completely factored. That's a completely factored. That's kind of nice. So I'm going to do the exponent first. I'm going to leave the 5 here. And then I'm going to FOIL the a minus 2 times a minus 2. I'm going to do first a times a, which are a squared. A times minus 2 is minus 2a. Minus 2 times a is minus 2a. And minus 2 times minus 2 is plus 4. So I can get k of a minus 2 equals to 5 times a squared minus 4a plus 4. That's doing the FOILing, combining like terms. And then I can do the multiplication by 5. And get k of a minus 2 equals to, I don't need the parentheses when I clear the parentheses, 5a squared minus 20a minus 20a plus 20. Not written very neatly. That's a non-factored answer. Usually when we have polynomials, we like to factor them. How would I factor that? To factor that, first I'd pull out a common factor of a 5. I'd go, this is 5 times a squared minus 4a plus 4. Then I'd factor what's left in the parentheses. I know my signs have to be minus and minus, and they have to multiply to positive 4, add to negative 4. It's going to be minus 2 and minus 2. And I can write that as the original problem. So that's why I said it would be okay to leave, because the original problem was completely factored. Multiplying it back out and refactoring it, I just get to where I started. However, multiplying this one out and factoring it, you don't get back to where you started, because it wasn't completely factored at the beginning, because you had, the parenthesis. It wasn't just one parentheses everything all multiplied. The plus signs between the terms made that not completely factored. However, if 30 was a test question and you took the time to multiply it out, something that started off factored, I'd probably give you complete credit for that, as well as that. Okay. A little bit of review here for the beginning parts of 31 through 42. And it's a review of section 3.2, I believe. I'm given a function which is just a special type of relation. This function is called f. The second function is called g. It's super easy to find a domain and range when a function is given as a set of points. And that's what 32 wants me to do. It wants me to find the function called g and find the domain of it. And if you remember from the last section, if you have a relation written as a set of points, the domain of a relation is all the x values. That's still the case when the relation is a function. So for 32, to find the domain of g, because it's a relation, of all functions are relations, they're just relations that don't have duplicate x's. To find the domain of a relation or define a domain of a function that's written as a set of points, you just take each of the x values and you put them in the squiggly set brackets. If it bugs you that that's not written in ascending order, then it's completely okay, but not necessary. You'd get full credit for this answer and that answer. These are both okay. So when you're writing the domain or the range of a relation or a function that's a finite relation or a finite function that's just defined by some points, it doesn't matter if you write the numbers in ascending order or not. To find the range of g, the range of a relation is just the y values, and functions, you'll never have duplicate x's, but you can have duplicate y's. That's okay in a function. It's just not okay to have duplicate x's. So for this range, I can say it's -2, 6, 17, -2, and 4. It's probably not the best answer, but I'd give you full credit for it. It would be better if you wrote the numbers in ascending order and didn't write the -2 twice. So this is, again, this is okay for an answer. This is better. We say the range is -2, 4, 6, and 17. For me, that's better, but I'd give you credit for both, especially on a test. Sometimes you won't even notice that there's duplicate y's in a range, and it's just not that big of a deal. It's not wrong. I wouldn't take points off for it. There is one teacher on this campus, GCC North, that I know would take points off for that because it's not kind of the most simplified version of the answer. Even though it's not incorrect, it's not simplified as much as you can simplify it, and there is definitely a teacher that would take points off for that, but I'm not that teacher. So the next questions that involve the f and the g function aren't particularly hard in that they don't have algebra, but they may be hard because you just don't know what they're asking. And there's two styles of questions. And in these questions, that if I'm given these functions, they're either, the questions are one of two types, and then you have to figure out which type they are to get the correct answer. So either, the problem gives you an x value, and it wants you to find the corresponding y, or the problem gives you a y value And it wants you to find the corresponding x. None of these problems are going to require any algebra. So the four problems, 36, 38, 40, and 42, that are staring at me right now, the whole key to the problem is first knowing what function they're calling out, and that's easy because I see the letter. The second is, does the number they give me stand for a y and it's asking me to find an x value, or is the number they give me an x and it wants me to find a y value? And it's super easy with function notation, because in function notation, any number inside a parentheses stands for an x. So for this style of problem, for the problem to give you an x value and wants you to find a y value, the given number has to be inside a parentheses. So both problems 40 and 42 I classify as a problem that gives me an x value and it wants me to find a y value. There's no algebra to do for problem 40. There's no algebra to do for problem 42. When I look at this problem, this asks me to find the y that corresponds to x equal to 2 in the f function. So because the number's inside a parentheses, it stands for an x. Problem 40, the 2 that it gives me is that 2 right there. That's an x equal to 2 in the f function. I'm supposed to find the y that corresponds to x equal to 2. And I could just write f of 2 equal to 3. Or if I want to, I can write y equal to 3. So the answer to problem 40, the important number you need is the number 3. Its kind of brother or sister problem, the one beneath it, g of negative 1, that negative 1 stands for this x. It's number inside the parentheses, so it stands for an x, and it's in the g function, so it's that negative 1. And the y that corresponds to negative 1 is y equal to 17. For problem 42, a correct answer would say g of negative 1 equal to 17. If you want to, you can say y equal to 17. So problems 40 and 42, because the number that's given is in a parentheses, that number stands for an x, and they're asking me to find the y that corresponds to the x. In the other two problems, 36 and 38, if a number's to the right of an equal sign, it's a y value. So for these problems right here, the number is going to be to the right of the equal sign. And if, using function notation, the number's to the right of the equal sign, it stands for a y value. So both problems 36 and 38, the number that's given is a y value, and I'm supposed to find the x that corresponds to that y. So there's no algebra, but if I was doing find the value of x in f of x, where f of x is 2, the 2 that problem 36 is calling out is that y equal to 2, because numbers to the right of an equal sign in function notation are the y that corresponds to a specific x. And in 36, the x that relates to y equal to 2 is x equal to 1. It wouldn't be wrong to say f of 1 equals to 2 because the number inside the parentheses is an x, the number to the right of the equal sign is a y. Ultimately, I need to see a 1 for problem 36. And for problem 38, just like problem 36, because the number in function notation is written to the right of an equal sign, it stands for a y value. The number out of all these sets here that 38 is given me, 38 is given me that y equal to 4. The number to the right of the equal sign is a y. It's very specifically that y. I'm supposed to find the x that corresponds to that y. And that answer is going to be x equal to 6. And then again, if I want to use function notation in my answer, I could say g of 6 equals to 4. 6 is somehow the important number. Okay, I keep going. And The next few problems are review from chapter 2, I think right in section 2.1. They give me a fraction but in function notation and want me to find the domain of a fraction and write in interval notation as opposed to words. I'm not opposed to words, but I'll do interval notation and words just because it asks for interval notation. We have to remember how to find the domain of a fraction, whether it's a function or not. To find the domain of any fraction, and you may remember this, but you might have forgot already, we ignore the numerator. We solve where the denominator equals to 0, and then we write our answer, either in words or interval notation. Here it asks for interval notation, so I'll be careful to give it, but if you give it the domain in words, I'd live with that. So in this problem, I'm finding the domain. It's a function notation that has nothing to do with the domain computation. It just tells me that this is a function, which means it would pass the vertical line test. So I'm going to ignore the 4. I'm going to solve the x minus 5 equals to 0. I'm going to add 5 to both sides. And I get x equal to 5. If I wrote x equal to 5 for an answer, I'd lose a couple points on a test, definitely. If I wanted to write the domain in words, I can say the domain is, I'll be lazy, all real numbers except 5. That would be a perfect answer in terms of I wouldn't ding you any points on the test, but it's not what's asked for. What's asked for is a domain in interval notation, and to do a domain in interval notation, you create a number line that has negative infinity on the far left edge, positive infinity on the far right edge, any number you're excluding from the domain between the infinities, make round parentheses, and the domain in interval notation, and that's what's asked for, would be the interval from negative infinity to 5, and then again the interval from 5 to infinity. Let me pull out my calculator, and I'll take that back. I don't have a graphing calculator with me today. I don't know what I did with my graphing calculator. I seem to lost it over the summer, which is kind of unfortunate because I wanted to show you something here in a couple minutes. I'm just not going to be able to show you, but it is what it is. If I had my graphing calculator, which I don't, and I graphed this function, the graph would look pretty close to this. It won't be exactly like this, but it'll be reasonably close to this. In college algebra, you learn how to graph things like this. That's kind of how the graph would look. Pictorially, for those of you that are visual, when we say the domain is all real numbers except 5, if you drew a vertical line through 5 on the graph will exist everywhere to the right of that vertical line and everywhere to the left of that vertical line, but no graph will cross or touch that vertical line. So pictorially, the domain of a fraction graphs get broken up into pieces, and if the domain is excluding one number, there's going to be two pieces, and the graph will exist on either side of that number we're excluding from the domain, but it won't exist at that number, for what it's worth. 46 is so easy it's hard. So again, it's a fraction. To find the domain of the fraction, because that's what I'm asked to do here, I'm going to ignore the numerator 6. I'm going to solve the denominator equal to 0, and then I'm going to write my answer. Unfortunately, there's nothing to do, and students a lot of times when there isn't nothing to do, they try to do something. The solving p equal to 0, it's already solved for. The p is isolated. There's a number to the right of the equal sign. That's the number I'm excluding from the domain. So when I write my answer, if I wanted to do it in words, I'd say the domain is all real numbers except 0. Or interval notation, because that's what it's asking for, I'd create a number line that had negative infinity on the far left edge, positive infinity on the far right edge, 0 between, and I'd write the domain in interval notation is the interval from negative infinity to 0, all round brackets, and 0 to infinity. And again, for those of you that are visual, the graph of this, if I had my graphing calculator, I should have done it differently, would look something like this. If you had a graphing calculator and you tried to graph it, you'd get something like that. Where, and again, the reason I say the domain is all real numbers except 0 is because if I find 0 on the x-axis, the graph won't exist. If I draw the vertical line through 0, the graph won't exist and will never go through that vertical line that goes through 0, but it will exist everywhere to the right of that vertical line and everywhere to the left of that vertical line. You don't need the graph to be able to find the domain of a fraction, but for those of you that are visual, that's what a domain of all real numbers except 0 can look like in terms of a graph. 48 wants me to find the domain of a fraction. And to find the domain of any fraction, I'm going to ignore the x minus 1. I'm going to solve the x plus 3 equal to 0, and then I'm going to write my answer. Fortunately, solving x plus 3 equal to 0 is kind of mindless. There's no square, so I don't have to worry about factoring. So I can say the domain is all real numbers except negative 3, or if I wanted to do a number line interval notation, I'd create number lines that had negative and positive infinity on the edges, negative 3 between them. In interval notation, the domain is negative infinity to negative 3, union negative 3 to infinity. And again, for those of you that are visual, if I had my graphing calculator, I'd graph this. Pictorially, the graph is going to look something like this. Trying to do this properly. Yeah, like that. And this. So again, pictorially, the graph is going to exist everywhere to the left of a vertical line through negative 3 and everywhere to the right of a vertical line next to the right of negative 3. The interesting thing is, if you solve the x minus 1 equal to 0, graphically it's going to give you the x-intercept. On fractions, when you set the numerator equal to 0 and you solve it, the point of the graph you get is the x-intercept, which has nothing to do with the domain. The domain of a fraction is kind of the vertical line that separates the graph into halves, and the vertical line that would separate this graph into halves is the one through negative 3. So those are the harder domain questions, but not the domain questions that when I give a test that students students usually don't miss points on those. But on problem 50, okay, I hear. That's not a problem at all. Thanks. Security came and visited me. They see me talking to myself and they think they need to get somebody to take care of me, I guess. So, in the rest of the problems that we have left to find the domain, they're polynomials. 50, 52, and 54 are all problems that aren't fractions. They don't have square roots. And, oh, suck. That just can't be good. Apparently they're testing the fire alarms, so hopefully my mic is kind of sucky enough that you're not getting blasted by that. I really don't want to end this video with just 5 minutes left. So for problems 50, 52, and 54, they're not fractions. They're probably appropriately called, they are polynomials. And there's no algebra to find their domain. For our purposes, the domain of any polynomial is all real numbers or the interval to from negative to positive infinity. The domain of any polynomial, and to be a polynomial, you have no x's and denominators of fractions, and if you have exponents, they're only positive integers. The domain of any polynomial is, in interval notation, negative to positive infinity, and in words, all real numbers. So, real quickly, I'm going to write the answers to 50, 52, and 54 down, and then I'll show you visually on 50 and 54 how the graph looks and how the algebra could let you down. So, the answer for problem 50, it's not a fraction, it's a polynomial. In words, I can write the domain is all real numbers. And in interval, I'm going to write negative to positive infinity. I'm going to do the exact same thing for 52 and 54. And then I'm going to relive 50 and 54 by showing you what the domain, pictorially, what the graph looks like, and if you did algebra, what the algebra, how it's going to let you down. So 50, it's actually going to graph to be a line. 52, the big distinction, even though it has the square, it's not a fraction. And for this, the domain is going to be all real numbers without an except. If I want to do interval notation, the domain is going to be negative to positive infinity. And there's nothing to do. If I do any algebra, I'm going to get an answer that doesn't belong in the domain. And I'll talk about 50 and 54 in a second. And then 54, similarly, the domain is going to be all real numbers. Or, in words it's all real numbers. In symbols, it's negative to positive infinity. You don't have to have a better understanding than that. Domains of fractions, you have to do algebra. The algebra is setting the denominator equal to 0. Domains of polynomials, there is algebra to do, or no algebra to do. And let me just maybe do 50. This is kind of overkill. I'm done with 50, 52, and 54. There isn't anything to do. But to help you maybe understand this, let me graph. Number 50 to help you understand the domain. answer, which is negative to positive infinity. So function notation for me is not the best notation when it comes for graphing. Anytime I have function notation, I am absolutely welcome to change the function symbol to the letter y. If it's easier for me to use the letter y, then I'm going to do that switching. So both of these will have exactly the same graphs. Function notation, it makes it easier to ask you certain questions, but it makes it harder to do certain things too. It makes it harder to graph. So the graph of m of x equals 2x plus 4 and the graph of y equal to 2x plus 4 are absolutely the same. So I'm going to graph y equal to 2x plus 4. That's the same as this graph. And that's just an easy line. So what I start off doing is I'll plot the y-intercept at 0, 4. And then I'll find the slope. The slope is 2, but that's not very good because it's not a fraction. So I'm going to write the slope as 2 over 1. And I'm going to go up 2 and write 1. So if I go up 2 and write 1 and do it again, up 2 and write 1 and do it again. I can't do it again, but I can go down 2 and left 1, down 2 and left 1, down 2 and left 1. So here's a graph with way more points than I really need to get. But that is what the graph of m of x equals 2x plus 4 looks like. Question is, how would you find the domain of that graph? Well, we know how to find the domain of a graph. We extend it. I'm going to extend it down and to the left and up and to the right. When I extend it down and to the left, it goes to the far left edge of the x-axis, the bottom of the y-axis. We did that in section 3.1. And up and to the right, it goes to the top of the x-axis, to the right edge of the x-axis, the top of the y-axis. So this would be a graph. If I was given the graph, I could find a domain because I would just find the far left point and its x-coordinate and the far right point and its x-coordinate. So when I said the domain is negative infinity to positive infinity, that relates perfectly to the graph of this equation. And there was the answer that I wrote. If you did algebra, the most tempting algebra to do is to take the problem and set it equal to 0. If you set the problem equal to 0 by minusing 4 from both sides and dividing by 2, the number that you're going to get is the x-intercept. And if you include that negative 2 in the answer, then you're either saying the negative 2 is at the left edge or the right edge of the graph, or it somehow divides the graph into parts, which it does none of those. And each of the problems, 52, 54, and 50, 52, and 54, if you are staring at the graph, you could extend the graph and get the domain this way. It would be negative to positive infinity. And more than that, if you did any algebra, the algebra is going to give you the intercepts. Like I don't have my graphing calculator, but I know how to graph x squared minus 16. The graph of x squared minus 16 looks like this. And actually, when we do chapter 5, you'll learn how to graph this yourself without using a graphing calculator, and it's not terribly hard to do. The graph of x squared minus 16 looks more or less like that. That's what the graph looks like. And again, if I wanted to find the domain of this graph, because it goes on forever, I'd extend it up to here. It'd go to the point positive, positive infinity. Up this way, it'd go to the point negative, positive infinity. And the domain would be the x-coordinate of the far left point, and then the x-coordinate of the far right point. It would be negative to positive infinity, like I wrote when I did the domain of this. Didn't do any algebra for it because it wasn't a fraction. I knew I could find the domain without algebra. If you did this algebra and you set x squared minus 16 equal to 0 and you solved it, you'd get the x-intercepts of the function, And the x-intercepts, unfortunately, have nothing to do with the domain of almost any problem, because they're generally not a breaking point like they are in graphs of fractions, or they're not at the far left or the far right edge. So real quickly, I know you're not wanting to see this, but if I made up like 4 problems or 6 problems and I said find the domain, and if I did f of x equals to 3 over x minus 4, g of x equals x squared plus 6x plus 1, h of x equals 5 over x plus 1, k of x equals 3x plus 2. Here's 4 functions that I randomly made up. For each one of these, if I wanted to find the domain, I have to determine if there's algebra or not. F of x is a fraction. The algebra to find the domain is to set the denominator equal to 0. The domain for this f of x function, if I wanted to do it quickly in interval notation, would be negative infinity to 4, union 4 to infinity. G of x, it's not a fraction. If I did any algebra, what I'd find is not a number that belongs in the domain, but I'd find an x-intercept. H of x, because it is a fraction, I need to take the denominator and set it equal to 0. The domain for h of x would be negative infinity to negative 1, union negative 1 to infinity. And k of x, because it's not a fraction, its domain is going to be negative to positive infinity. So in this section, there are 2 distinct kinds of problems that gave me equations that asked me to find the domain. Fractions, we did in chapter 2. We take the denominator, set it equal to 0, ignore the numerator. Polynomials are new to this chapter, and there's no algebra to find the domain of any polynomial. If we have an x and no fractions, generally the domain is going to be all real numbers or negative to positive infinity. Almost done. I'm doing 56 and 57 because there's only 3 of these styles of problems, and I didn't think 2 was enough, so I thought I'd do an odd problem. So none of these problems are in need of any algebra, so they go quickly if you understand what you're looking for. Every single problem is either calling out a point on the graph or wanting me to find an x or a y coordinate. So part A for 56 asks me to find an x-intercept. To find an x-intercept, I look at the x-axis, I go across the x-axis, and any point that's on the x-axis is considered an x-intercept. So for this graph in 56, the x-intercepts are the points negative 1, 0 and positive 5, 0. Part B asks me to find a y-intercept. To find a y-intercept, I look at the y-axis, and any point that's on the y-axis is a y-intercept. And that point 0, negative 5 is supposed to be on the y-axis, so I'm going to call it a y-intercept. The last 2 questions are the kind of questions where I have to understand if the number given is an x value and it's asking me to find a y value, or if the number given is a y value and I'm asked to find an x. In part C, because the number is outside or after the equal sign, it's a y value. So in part C, the 7 that's given is this y equal to 7, and I'm supposed to find the corresponding x value to y equal to 7. The answer to part C is going to be x equal to 6. In part D, because the number that's given inside of parentheses, it stands for an x value, and I'm supposed to find the y value that corresponds to it. So the 4 parts of 56, x-intercepts are points on the x-axis, y-intercepts are points on the y-axis. When I'm given a question about a function and I have a number, the number's to the right of an equal sign, it stands for a y value. I'm supposed to find that point that has that y value and find its corresponding x value. If the number's inside the parentheses, it's an x value. I'm supposed to find the corresponding y value. Last one. And then the rest of the sections in chapter 3 are short. And in the beginning of chapter 4 are some short sections as well. So same, essentially 4 questions, except I called this function h as opposed to k. And it might be a tough read, so I'll blow it up just a little bit, but hopefully you have it in front of you as well. So x-intercepts are points on the x-axis. You can't barely read the points because they're on the x-axis. But the x-intercepts are that point and that point because they're on the x-axis. And they're the point -4, 0 and +2, 0. Y-intercepts are points on the y-axis. That's the point 0, 8. The next 2 questions give me function notation. I have to understand if the number that's given is an x or a y. If it's to the right of the equal sign, it's a y. If it's inside of parentheses, it's an x. So the number here is a y equal to 0. So part C is calling out that y equal to 0 and that y equal to 0. So the number in part C that's given, the number 0, it's to the right of the equal sign. It stands for a y value. I'm supposed to find any x's that correspond to that y value, and the x's are going to be x equal to -4 and 2. So the answer to part C is going to be x equal to -4 and 2. Part D, the 0 that's given is an x value because it's inside of parentheses. So the point that part D is looking at is at point 0, 8, and it wants me to find the corresponding y value. And I can say h of 0 equal to 8, or if I want to, I could just say y equal to 8. I don't think the last 2 problems that I did, 56 and 57, find their way onto the test. I can't remember testing on those recently, so they're not probably the most important, but they come up again in college algebra, math 150 or 151, so I just felt like doing them even though I might not test on them. Alright, so that's the last long section for chapter 3. Next time I lecture, I'm going to do section 3.4, which is a short section, and 3.5, which is a short section, but it's a short word problem section. They're not bad word problems, but some students just kind of get intimidated by word problems in general. So if you don't have a negative attitude towards those word problems, they're just not that bad. If you did well on the word problems on the last test, like the boat problem or the walking and running problem, even though these are completely different word problems, they're just not bad word problems. If you did well on those word problems, then you'll do well on these word problems again. These are almost a little bit easier. All right, I'm going to stop this, and hopefully you're still awake.